Welcome back to Calculus 2. I'm Dr. Jeff Groh. Today, we're going to talk about differential equations. A differential equation is an equation involving the derivative of some function that is not explicitly given. So, for example, suppose I write down what is called the natural growth law. The natural growth law says the rate at which a population grows is proportional to the population size. This should make a little bit of sense. If I were to lock 1,000 people into a building and give them everything they need to survive for 10 years, at the end of 10 years, would you still have 1,000 people in that building? Or might you have more? It depends upon how well they like each other. But if I did the same experiment with 1,000,000 people in a city over 10 years, at the end of 10 years, would I still have 1,000,000 people locked in that city? Or might I have proportionally more than the 1,000 people in the building? I think you can see the rate at which the population grows will depend upon how big that population is. Rate, whenever you hear the word rate, you're thinking of derivative. The rate of change of the population with respect to time is exactly the derivative of the population with respect to time. When I say the rate of growth is, that means equals an equation already, proportional to, there has to be a constant of proportionality, the population size. The constant of proportionality will depend upon the particular population. Some populations will have larger or smaller growth rates than others. So the constant has to be determined by experiment. Now, I have this equation, but this equation does not tell me what the function p is. It just tells me a relationship the function p has to satisfy. However, on this particular simple example, we can easily solve this. There are other differential equations that are much more difficult to solve, and that's why we have a whole course titled Differential Equations. This one we can solve. Let's start with our differential equation dp dt equals kp. We can separate variables by multiplying both sides by 1 over p. That just leaves a constant k on the right. If we then multiply by dt on both sides and integrate, you can see what's going to happen. On the left, we're just integrating 1 over p dp, and that's the log of the absolute value of p, plus maybe a constant of integration. On the right-hand side, we're integrating with respect to t, so we get kt plus another constant of integration. We have these two things equal to each other. We'll move the one constant to the other side. When you combine two arbitrary constants, you get an arbitrary constant. You can see then we have log absolute value of p equals kt plus c3. It becomes tedious writing these different constants. Let's adopt a convention that all of these arbitrary constants will just be called c. We would like to solve for p. That was the whole point, is to try to figure out how the population grows as a function of time. We need to get rid of the things surrounding p, starting with the thing furthest away by the order of operations agreement, namely the log. To get rid of a log, you need the natural exponential function. So we take e to the power of both sides. The log and the e cancel on the left. Note that if I take a to the power of b plus c, that gives me a to the b times a to the c. So on the right, I get a to the kt times e to the c. E to the power of an arbitrary constant is an arbitrary positive constant. We'll just call it C, but it's an arbitrary positive constant. But how do you solve an absolute value equation? As long as A is positive, the absolute value of x equals A is solved by x equals plus or minus A. So we get P is plus or minus this arbitrary positive constant e to the kt. But plus or minus an arbitrary positive constant is an arbitrary constant. So we get P equals C e to the kt, and we get what is called a one-parameter family of solutions. There's not just one solution. There's infinitely many. After all, in order to solve a differential equation, you have to undo a derivative, meaning you have to integrate. And when you do, you get a constant of integration. That's going to come somewhere into your solution. For us, it ends up being this constant parameter C. So we don't just get one solution, we get a one-parameter family of solutions. You can even see that C equals 0, total extinction, that is a solution, and even negative population values will be analytical solutions to the differential equation. Of course, negative population values don't exist in reality. In order to nail down the constant of integration, we need to know one more piece of data about the curve. If I specify a particular point, P0 on the TE plane, that will give me one curve that passes through that point. This is called an initial condition. It's sometimes expressed as the differential equation together with an initial condition. The population at time T0 is P0. This is called an initial value problem. When you give a differential equation together with initial data, you have an initial value problem. The initial value problem determines the constant of integration. Let's adopt the initial condition. The population at time 0 is some value P0. In the case of locking 1,000 people into a building, P0 would be 1,000. In the case of locking 1,000,000 people into a city, P0 would be 1,000,000 at time 0. That is the initial population size. The constant C usually has some kind of physical interpretation. Let's see what it is under this specific assumption. We'll get P0 equals C e to the k times 0. We're choosing t equals 0, plugging it in, and outputting the value P0. As you can see, the constant of integration C is the initial population size. So we can do better than this. We can say the population is the initial population size times e to the kt. This is the solution to the initial value problem. Let's write down another differential equation, Newton's law of cooling. Let's suppose I take a batch of cookies out of the oven. They might come out of the oven at maybe 350 degrees. But as they cool down, the temperature should go from a very high value towards room temperature. The closer it gets to room temperature, the slower the rate of cooling. The rate at which an object cools, the rate of change of temperature with respect to time, should be proportional to the difference between the ambient air temperature minus the temperature of the cooling object. You can see if the gap between these two is large, if the ambient temperature minus the temperature of the cookies is very large and negative, you'll get a negative slope and the temperature will decline. This also works for warming. If the temperature is less than the ambient temperature, then this difference will be positive and the temperatures should increase. When the temperature gets to the ambient temperature, you don't change temperature at all. It just stays constant because The derivative equal to 0 implies the function is constant. We'll also have some initial temperature. So we have the ambient temperature, the initial temperature at time 0, and this differential equation. This gives us an initial value problem. How do we solve this initial value problem? First, we'll solve the differential equation. If we start with the differential equation, we can separate variables by taking 1 over Ta minus T, Ta is a constant, times dt equals k times dt. Integrating both sides, the right-hand side is simple enough, kt plus some constant of integration. We won't include a constant of integration on the integral for the left-hand side because we'll just end up combining it on the other side anyway. We're missing a minus. This is almost in the form of the integral of f prime over f. The derivative of the denominator is minus 1. So I'll put a minus here and get minus log absolute value, Ta minus T. No plus C because it's already on the other side. If I write this as Kt plus C, I need to solve for T. So I start with the thing furthest away by the order of operations agreement, the minus. You have to get rid of the minus first. So I multiply both sides by negative 1. I'll get log absolute value of Ta minus T equals minus Kt. Now technically it's going to be minus C, but minus an arbitrary constant is still just an arbitrary constant. Do you see how we can play fast and loose with these constants of integration? Next, we get rid of the natural log. That requires an exponential function, so we take e to the power on each side. So we get the absolute value of Ta minus T equals e to the minus kt times an arbitrary constant of integration. We can even get rid of the absolute values and absorb the plus or minus into the C. We're still solving for the temperature, T, so we'll move some terms around. We'll get the temperature is the ambient temperature minus C, I can just write plus C, e to the minus kt. Again, playing fast and loose with those arbitrary constants of integration. This gives me a one-parameter family of solutions. Notice that the second term is called a transient term. It decays exponentially with respect to time, meaning as T goes to infinity, the temperature tends towards the ambient temperature. But wait a minute, we need to determine the physical significance of the constant of integration. Remember, the temperature at time 0 is some given value, T0. So for instance, on the cookies, T0 would be 350 degrees, the temperature as they came out of the oven. So I'll put T0 equals Ta plus C e to the 0, since I'm plugging in time t equals 0. This is of course 1. It follows then that the constant of integration is the initial temperature minus the ambient temperature. Therefore, T is going to be Ta plus T0 minus Ta times e to the minus kt. K is called the cooling constant. It can only be determined by an experiment. It changes depending upon the nature of the cooling object or the warming object. This is then the solution to the initial value problem. This just solves the differential equation without reference to the initial data. You could spend the rest of your life learning how to solve differential equations. In fact, the subject is an area of specialization within mathematics. I only want to do one more little thing. I want to show you how to approximate solutions to initial value problems. Quite often, you will encounter some differential equation you have no idea how to integrate. If that's the case, hope is not all lost. You may still try to find approximate solutions to the differential equation together with the initial condition. Let's suppose that we start off with the differential equation. dy dx is some function of x and y. And let's suppose that we have initial condition y of x naught equals y naught, meaning that the point x naught, y naught is a point on the solution curve. There may be a foliation of the plane consisting of solutions. We want the one that passes through the point x naught, y naught. Let's also suppose that the differential equation is so complicated you have neither the will or the ability to solve this analytically. So what we'll do is we'll approximate the derivative. dy dx is approximately. How do we do that? We'll start at x naught. From there, we can follow a straight line. How far? Not too far, because the straight line doesn't closely match the curve, especially if you go too far. But if we go just a short distance, then the gap will be small enough that maybe we can ignore the errors involved. We'll go from this point, x naught, y naught, to another point, x1, which is x naught plus a little bit, and then y1. But where is that y1? Well, it depends upon the slope of the curve. What is the point slope form of a line? Well, we get the following. y1 minus y naught divided by x1 minus x naught, which is h, is, well, the slope of the curve. But the slope is determined by this function at the point x naught, y naught. We just solve for y1, and we have y1 is y naught plus h times f of x naught, y naught. We'll put that in a little bucket. Once we have y1, we can approximate the slope there and shoot a little ways away, and hopefully we won't be too far when we get to x2. y2 is going to be y1 plus h times f of x1, y1. And we keep going in this way. In general, we get something called Eulers Method. After Leonhard Euler, the most prolific mathematician of all time, he did his work in the 18th century, the 1700s. He was very prolific, producing hundreds of articles over the course of his lifetime, and even hundreds after he died. People searched through his notes and produced a lot of papers from his notes after he passed away. He was prolific in more ways than one. He had 13 children. So yes, he was prolific in more ways than one, and he continued to publish new work in the last 2 years of his life, despite the fact that he was totally blind. His method is, we approximate the solutions to the differential equation by yn plus 1 is yn plus h times f of x in yn. Let's try this out. I want to look at the Freedman equation from Big Bang cosmology. It goes like this. There's an expansion factor of the universe, which we'll denote by y. Its rate of growth is squared, is a constant divided by y minus another constant. The constant k can only take values in -1, 0, and 1, and represents a sort of undilated spatial cross-section of the universe. We dilate the universe so we can vary the curvature at different times by an expansion factor, which is given by this y. So we only take k to be -1, 0, and 1. A can only be determined empirically, but let's just assume that a is 1. We'll choose units on the value for y so that a equals 1. That way, dy dt will be plus or minus the square root of 1 over y minus k. Now, which is it? Is the universe expanding or contracting at the present time? from all that we can observe now, it looks like the universe is expanding. It's getting bigger. So we'll take the plus to begin with. We also have maybe some initial time. The universe has some initial expansion factor. Why not? Let's choose this to be 0.1, and let's choose h to be 0.01. And then we'll try to find different values for that expansion factor as we go on. The function f of, in this case, t comma y is on the right-hand side. So we get yn plus 1 is yn plus h times the positive square root of 1 over yn minus k. We'll use this formula to try to see what the solutions to the Freedman equation look like in Big Bang cosmology using different values of k. At this point, I really do need to use my computer. Remember the initial values though. The initial expansion factor is 1/10, and we're using h equal to 1/100th. Here I've opened up an Excel spreadsheet. I'm going to put times the expansion factor y. We need also our h value. The initial time is 0, and the initial expansion factor was 0.1. H was 0.01. To get to the new times, we take the old times plus h. But we have to convert the h's to an absolute reference and leave a2 here as a relative reference. To show you what I mean by that, let me paste this down for a little bit. When I click on the cell A4, I still get C2 because of the dollar signs, but I now get A3. If I go to the cell below that in A5, it now says A4. You can see it's using a relative reference, the cell above for the A4. But C2 is an absolute reference, always referring to the contents of this particular cell. So let me get rid of all of that. Let me come over here and show you how to update the y's. The updated y's are going to be determined by Euler's formula that we just wrote down. It's going to be the old y plus h, which must be, again, an absolute reference, so it needs dollar signs, times the square root of 1 divided by the old y minus k. I'll put the k right over here. We'll choose k equals, say, 0 to begin with. There's one little correction I need to make, and that is I need to put dollar signs around the constant k. Now, we're going to paste this down. Dragging these down would take a lot of effort. I don't want to do that much effort. So here's what I'm going to do. Instead of dragging these down like this, I'm going to hit Control G and go down to cell A1002. Yep, I'm going to go way down there. We could go to A1,000,000 if we wanted to. A1002. Now it's very important you don't click anything yet, but you press Shift and then click right there. And then hit Control D, and that pastes the formula all the way down. You want to see? We've just pasted that formula all the way down to the bottom. So into row 1002. That's way down there. Now I'm going to graph this. I'll click on A and then press Shift and click on B. Hit Insert, and then here's my chart right there. You see that chart? There's your chart for k equals 0. You start growing pretty fast, but you get slower and slower growth rates, but still a positive growth rate forever. That's with k equals 0. The spatial cross-section of the universe has curvature equal to 0. If the curvature is -1, notice it goes very, very flat very quickly. It does change a little bit, but it is asymptotic to a straight line if the spatial cross-section of the universe is -1. So there's a bit of a difference between k equals 0, which always slows but always increases, and k equals -1, which always tends towards a linear growth rate. There's only one possible value to observe otherwise, and that's k equals 1. Notice that we go off of a cliff here. Something went wrong with our calculation. Let's go down and see if we can figure out what went wrong. There it is. There's the problem. And you can see what's going on. We got y to be greater than 1. Let's look at what would happen with y greater than 1. With d2 having a value of +1. If y is greater than 1, 1 divided by y is less than 1. And if we take something less than 1 and subtract 1, we get a negative value. And that's a problem under a square root. So the problem is we leveled off. You can see on our chart above, the slope is leveling off and going to 0, and then all of a sudden it crashes. What should happen is we should change the sign of the square root. Let's see, where were we? Right here. We need to change this from a positive square root to a negative square root, and we'll paste that down to the end. You can see it didn't make it all the way down to the end because something else happened. But if I go back to my chart, you can see that the universe expands to some maximum value, levels off, and then catastrophically contracts until it reaches the big crunch. Once you go beyond the big crunch, you can't get any smaller than that, any smaller than a size 0, all points in the universe crashing to a common point. And we get a problem with our mathematics beyond that. Let's see where that occurs. Down here. There it is. So what's going on? You can see y goes negative. And if y goes negative, you get negative -1, it's negative, onto the square root again. And so you can't do anything with the analysis beyond the big crunch in the Freedman-Robertson-Walker Big Bang cosmology. There it is, 3 fates for the universe. If you have a spatial cross-section of the universe that is 1, you end up with a maximum expansion and then collapse to a big crunch in finite time. If k is either 0 or -1, the universe will continue to expand forever, but at slower and slower rates. If k is -1, the expansion factor tends to grow at a linear rate as time goes by. Notice that we did not get analytic solutions to the Freedman equation. What we did is approximate solutions to the Freedman equation using Euler's method of approximation. Using Euler's method, we were able to see different outcomes for the universe as predicted by the Freedman equation in the Freedman-Robertson-Walker Big Bang cosmology.